All right. This is an introduction to correlation. Well, a recall of correlation and an introduction to linear regression. So I want you to recall from our last lecture in section 5. Now remember we're in section 8. It's been a little bit because we had a midterm in between. Uh, we want to recall that correlation is just because two variables are related does not mean they cause one another. Correlation does not mean causation. 3 types of correlation: positive, negative, and none, determined by the correlation coefficient R, which we find is equals CORRELXY in Excel or Sheets. It's between -1 and 1. It has a way of being categorized by strength, seen in this chart. So take a minute to reflect on this chart. Negative numbers would indicate a negative correlation. Positive numbers are a positive correlation. That's why this is the range of absolute correlation coefficient. It's taking away the negatives. It's just giving us the ranges, whether it be negative or positive. This is what a positive correlation looks like. We'll be looking at this specific example again in a minute. This is what a negative correlation looks like. This is what no correlation looks like. So linear regression is defined as a simple linear regression aims to find a linear relationship between the correlation between an independent and possibly dependent variable. We say possibly because we don't know if they're related until we calculate the correlation coefficient. The regression line can be used to predict or estimate missing values. This is also known as interpolation. It's done by hand. I'm still going to show you how to do it, but I'm still going to use Excel. And it's done by Excel and Sheets pretty easily. Or a calculator, but I'm not going to show you how to use the calculator because that is deprecated technology and we don't require TI-83s or 84s anymore. So we're not using that. If you want to look it up, YouTube, how to graph linear regression on a TI-83, 84, whatever model you have. So we're going to cut to linear regression by hand and using Excel to calculate the line sample problems. So the first sample problem we're looking at is the units produced being in the thousands and the total cost being in the thousands as well. So I've scaled down the data. This is all measured in thousands, but it's going to be easier to do when it's in scaled down. Our slope is this scary equation, and our y-intercept is this scary equation. This symbol, let me get the laser pointer. This symbol right here is sigma. So it means sum. So you're taking the sum of the x value times the y value minus the sum of the x times the sum of the y divided by the number of data points times the sum of the x squared minus the sum of the x squared. It's very complicated. Sum of the y's minus the slope times the sum of the x's divided by the n. So we're going to use Excel to figure this out. I'm going to show you how to do it quote unquote by hand, but I'm still going to use Excel because it's a lot of work and Excel will keep me organized better. So I'm going to back out of this, minimize this. I stole the definition, by the way, of linear regression from this website right here, Newcastle University. So in the spirit of full disclosure. All right, now we're going to look at Excel. I'm going to just open up the Excel. I'm going to zoom in a little bit so we can see better. All right, the first thing I need to do is I need to take my x times my y and multiply it by my n. So the first thing I need to do is take my x, so a2 times b2, that's 71. Now I need to pull that down. And now I need to sum that up. Equals sum of 1, 2, 3, 4. Come on. Come on. What's going on? Please don't freeze. Please don't freeze. Am I even recording? I am. Okay. Stop. Please. Thank you. Alright. So, our sum is 1257. Now I need to multiply it by 4. So that's our first number for our slope. I'm going to calculate that over here. 5028. That's our n times our x minus y. Now I need the sum of the x's. And I need the sum of the y's. And then I need to multiply those two numbers. So then we're going, whoops. Careful what you do when you are in the formula bar. A7 times B7, 4480. We're going to go, that's minus 4480. I'm going to put parentheses around this. I will have Excel calculate this in just a minute, but I am keeping track of my numbers. All right. I don't know how to get the ribbons back. Always show ribbon. There we go. I need that ribbon because I need to go home and I need to make this wrap text. No, I want that bigger. Sorry, we don't need any of that. Now I need to do the sum of the x squared. So I need another equals. I need the sum of the x actually I need this another set of parentheses in here, squared, enter. So that's 30, and then the sum of the x squared, which is 100. So this is times n, so that's 120. So this is going to be, parentheses, 120 minus 100. All right, now we're going to calculate it out. So our slope is 27.4. Now we need our y-intercept. So our y-intercept is the sum of the y, which is the 448 minus our slope times the sum of our x. Hold on. I need a parentheses here, a parentheses here, divided by 4. And our y-intercept is 41.45. So our model should be y, technically it should be y hat, because it's a model. 27.4x plus 41.5. So let's see how close we are. I'm going to now select my data, and I'm going to insert a chart. And I'm going to zoom out a little bit so that we can move this chart. This data looks approximately linear, so linear regression is possible here, which we should have did before we did all of this math, but it's fine. Now I'm going to click on the data. I'm going to right click on the data. I'm going to add trend line. Trend line and regression line are the same thing. Notice it says linear. I can do it in different types of data, different shapes of data, but we're only concerning ourselves with linear right now in this class. I will show you how exponential and logarithmic and polynomial make sense in graphing later on in this class. Now what I want to do is I want to display my equation on the chart and my r squared value on the chart. The r squared value, I can find the r from taking the square root of this, or I can do equals CORREL. And then square it. The r squared is just how good our model is. Look, it's 27.4 plus 43.5. I was so close. So close. This is better to do than by hand, because it took 30 seconds to do with Excel and entirely way too much effort by hand. So let's look at one more example. Let's recall our math and ELA scores. I want to come up with a model and then use that model to predict what my ELA score is based on my math score and my math score based on my ELA score. So I'm going to right click here and I'm going to format my trend line because I already drew this trend line in a previous example. I'm going to just display my equation on the chart. I don't need my r squared. I just want the equation. So the equation is y equals 0.9202x plus 7.0345. Now, if I were to want to predict a ELA score based on a math score, I'm going to substitute in for x. So say I got a 36 on my math test, and I want to know what my ELA score is based on that. So now I need the calculator. I need a smaller calculator. I don't need the history. I don't need to be reminded. I don't know how to do simple math. Come on. There we go. Clear. So we go 0.9202 times 36 plus 7.0345. Based on my 36 math score, I could expect my ELA score to be 40.16 for an ELA score based on my model. Now I could go backwards. Let's say I got a 100 on my ELA and I want to know what my math score is. I'm going to use this to solve. So let's go 100 minus 7.0345 divided by, so that's 92.9655 divided by 0.9202. I messed up. Hold on. 100 minus 7.0345 divided by 0.9202. There we go. I can expect a 101 on my math test. Now, here's a good example of correlation not causing causation. Okay, my math test and my ELA score are probably related under some other underlying variable. My math score does not actually impact my ELA score. It's probably my study habits, my attendance in school, or any other variable. But they are related, so I can use the model to kind of predict. Okay? I hope that helps.